Impulse momentum, Unit 4, Worksheet 1. So, we start with Newton's second law and we think about how a force causes a mass to gain velocity. Because really that's typically what we're mostly concerned about, right? We can't fully visualize what acceleration means quantitatively. Like, okay, something's accelerating at 20 meters per second each second. Well, that's pretty big acceleration, I can imagine, but ultimately, to be able to picture it in your head, you got to think about how the velocity is going to change. So, this trick with impulses, we start with the definition, Newton's second law, acceleration of an object is equals to the net force divided by its mass. The bigger the mass, the lower the acceleration. Therefore, if you were to start pushing both of these, one of these would achieve a greater velocity than the other, right? The smaller mass would achieve a greater velocity. So we'll see what that means. So what we do is we take definition of acceleration. Acceleration equals change in velocity over time, and we plug it in to Newton's second law. So we put in change in velocity over time for acceleration, and so we get force over mass equals change in velocity over time. We cross multiply, so the m comes up here, the delta t comes up here, and we end up with this equation. All right? Force times time equals mass times change in velocity. So the longer the amount of time the force acts for, the greater the object's velocity is going to end up being, the greater the object's change in velocity is going to end up being. And this is a really useful way. It's really just Newton's second law written differently. It's really just, we literally just put in the definition of acceleration and rearranged it a little bit. Now we give some names to these things. The product of force and time we call impulse. The product of mass and change in velocity we call change in momentum. All right, so that means momentum by itself. Momentum by itself would just be mass times velocity. All right, so when you have momentum, an object when it's moving has momentum. When it's moving, only when it's moving it has momentum. People called this inertia earlier in the year. Inertia is literally just mass. Inertia times speed, that's momentum. So momentum is, sometimes you say it is motion. It's literally anything that's moving is going to have momentum because anything that's moving has mass and it has velocity. We do use a symbol to represent impulse. J equals F delta T. Change in momentum equals M delta V. All right, so we do use a symbol for impulse here. And it's just force times change in time, capital J. I don't like to use this. It's confusing, right, because it looks like joule, right? So I really don't like to use the J very much. I really don't like that. I like to just call it force times time is impulse. M delta V is momentum. Whatever the impulse that's given to the object, right? So impulse is given, right? It's given to the object, and that results in change in momentum. Right? So impulse is given to the object by a force for a certain amount of time that results in a change in momentum of the object. All right? So this worksheet just kind of starts off some basic calculations, right? So impulse, I'm going to write them at the top here, equals force times time. We don't put the delta in front of time. Change in momentum, delta P equals M delta V. And at any time I can equate these two because impulse causes change in momentum. So force times time can equal M delta V. So that's, like I said on the previous page, momentum at some point in time is just given as the object's mass times its velocity. So sometimes we don't track the change in momentum. We just say, okay, what's the momentum of that object as it's moving through space? All right, so first of all, 10 Newton force acts on an object for 5 seconds to determine the impulse given to the object. All right, so impulse. And again, that's capital J, which I don't like, equals force times time. All right, so force equals 10 newtons. Time equals 5.0 seconds. Now, we got to get back to some basics here in solving problems, reading questions. A lot of your mistakes on the midterm came from just still not being able to read questions and identify what you've been given. So you really got to narrow in on what do these mean, right? It doesn't say necessarily a time of 5 seconds. It just says 4 or 5 seconds. So you need to be able to know that that represents a time. So the impulse then, right? I'm not going to use the symbol J because it really is just very confusing. 10 newtons times 5.0 seconds. Now, that would be 50, and the units are newtons times seconds, newton seconds, not newtons per second. We didn't divide the newtons by the seconds. We multiplied the newtons by the seconds. So it's 50 newton seconds of impulse is given to the object. This sounds a lot like energy, right? Like you do work on something and you give something kinetic energy, and that is true, and it does seem familiar, but it is different. It is different. It's a different concept here. It's similar though, because obviously this force did work, but the difference is I gave you the length of time the force was applied for, not the distance the force was applied for. So if I gave you the distance, you'd want to use work. Work equals force times distance. Work equals change in kinetic energy. Kinetic energy equals 1/2 mv squared. Now, you can see, right, there is a similarity there. K equals 1/2 mv squared, right? Momentum, P, is mv, right? So there is a relationship between the object's kinetic energy and momentum. You can't ignore that because these equations often get confused. In fact, you could rewrite kinetic energy, if you wanted to, as the momentum squared over twice the mass. So momentum squared over twice the mass. So that would be m squared v squared over 2 times the mass. Masses would cancel. You'd end up back at this, right? So you substitute that in for P. So that is another way to write kinetic energy. It's kind of interesting. We don't do that in introductory physics, really. But in upper level physics, this is often how you write kinetic energy, P squared over 2m. Anyway, they are related, but again, if I gave you the distance the force acts for, you'd use work equals force times distance. If I give you the time the force acts for, you do impulse equals force times time. Work causes a change in kinetic energy. Impulse causes a change in momentum. So a 0.5 kilogram lab cart starts from rest and is given a push from a student reaching a speed of 4 meters per second during the change in momentum of the object. So delta P equals m delta V, mass times change in velocity. All right, so the mass here, let's list out the variables here. Mass equals 0.50 kilograms, back to basics here. Change in velocity, it starts from rest, so V initial is 0. So that's V final minus V initial, which is 4 meters per second, minus the initial, which is 0 meters per second. So the change in velocity is plus 4 meters per second. This pen's kind of lousy. V equals plus 4 meters per second, change in velocity. So let me do the calculation over here. Delta P equals 0.50 kilograms times plus 4 meters per second. All right. Delta P equals 2.0, and the units would be kilograms times meters per second, which is the same as a Newton second. A Newton is a kilogram times a meter per second squared, so you would cancel out one of the seconds by multiplying that by seconds, and you would end up there. So we can use these interchange. So this is the interesting thing. I didn't mention anything about the force here. Right? Starts from rest and is given a push, so that is your force. So the impulse given to the object by this push is 2.0 kilogram times meters per second, or 2 Newton seconds, depending on which way you want to report it. All right, 0.14 kilogram baseballs on a tee is given an impulse of 9 kilograms times meters per second from a hit from a bat. Determine the velocity gained by the baseball. All right, so we practiced calculating impulse. We practiced calculating change in momentum. It's time to put them both together and say, okay, force times time equals mass times change in velocity. Where the force, there's no 4 here, the force is actually in the packet posted on the site. There is a number 4. We should probably look that up and write that in here. So the force we don't know, all right. Time we don't know. Oh, that's going to be a problem. Oh, no, it's not. The mass we know is 0.14 kilograms. The change in velocity we also don't know. Well, it seems like we don't know a lot, but what the heck is this? Oh, that's the impulse. So the impulse was 9.0 kilograms times meters per second. So that goes in for force times time. Since we don't know force times time individually, but we do know that that's impulse. So we put that in, 9.0 kilograms times meters per second equals 0.14 kilograms times the change in velocity. So we're solving for change in velocity, so we multiply both sides by 1.4 kilograms. All right, maybe I should write it again up here so you can see each step when you look at the solutions. So I multiplied both sides, divided both sides by 14. All right, so 9 divided, oh boy, calculator, 9 divided by 0.14 is 64. All right, and what are the units? Kilograms cancel, it's meters per second. I'm left with change in velocity. All right, so the change in velocity is 64, and it came out positive. This is a vector quantity. We do need to keep track of that. So 64 meters per second was gained. Very cool. All right, let's look at the next one, number 5. I'll try to do both 5. Oh, number 4 doesn't exist. It does in the other version, but oh well. Rocket at 0.1 gram. Oh, that should be kilograms. Darn it. Rocket launches off the ground, reaching a top speed of 75 meters per second in a time of 0.25 seconds. Determine change in momentum of the rocket. So, this is the mass, 0.10 kilograms, I should read, the speed, and the time. All right? Determine the change in momentum. So, delta P equals m delta V. All right, so the mass is 0.10 kilograms. Change in velocity is plus 75 meters per second. It's gaining, starts from rest, right? Launches off the ground, it would have to start from rest. So it would be delta P equals 7.5 kilograms times meters per second. So it gained 7.5 units of momentum here. All right, determine the impulse given to the rocket from the engine. All right, impulse, we said, is force times time. Well, I don't know the force. Force, we have no idea. Should have listed out the variables over here. Let me go back and put that in. So I don't know the force. I know the time is a quarter of a second. Right? The rocket engine blasts just really quick, just a poof, just a quick puff, kind of like an explosion, just launching it up into the ground. All right, really fast. Usually a rocket engine will fire for maybe a couple seconds, you know. But anyway, at least a model rocket like this intends to be. Well, I don't have force times time, but oh, remember, force times time equals change in momentum. So the impulse here is just that same number we already calculated. All right, there we go. Determine the amount of force the engine applies to the rocket. Okay, now I can say, okay, if impulse equals force times time, now I can say, okay, the impulse equals 7.5 kilograms times meters per second. All right, so 7.5 kilograms times meters per second. The force here, we don't know. The time is 0.25 seconds. Right? So then we divide both sides by 0.25. Right? And then we get F equals 7.5. So this would be basically 7.5 times 4 should be 30. Oops. 30, and the units end up being kilograms times meters per second, which is a Newton. Very cool. That's a fun little problem, right? So you kind of put it all together here. You know, you can observe the speed the rocket gains, right? And how long the engine fires for. And from that, you can deduce the force using this impulse momentum concept. This is really important stuff. Anyway, here we go. A 2 Newton net force is applied. Let me just check what the next page is here. Yeah, okay. Try to get up through a couple more here. 2 Newton net force is applied to a 3 kilogram block on a frictionless surface for 3 seconds. So, I should probably draw some pictures here. Positive 2 Newton net force applied to a 3 kilogram block, right? So we have this, we've got plus 2.0 newtons. It's a 3 kilogram block. The time is 3.0 seconds. Draw a diagram of the situation, including the forces. Oh, man, I really should have read that question first. Draw it a little nicer. 3.0 kilograms is the mass. The force is plus 2.0 newtons. There would be a normal force here holding it up. There would be a force of gravity pulling it down. Those would be balanced, right? 30 newtons would be pulling it down. Normal force would be positive 30 newtons holding it up. There's no friction, so there's no force going the other way. Impulse. All right, impulse equals force times time. All right, so the force is positive 2.0 newtons. The mass is 3.0 kilograms. The time is 3.0 seconds. So pretty straightforward, plus 2.0 newtons of force for a time of 3.0 seconds. That means the impulse given to the object is positive 6 Newton seconds. Positive 6 Newton seconds. All right, determine change in momentum. Well, again, delta P equals impulse. All right, just like work equals change in kinetic energy. Impulse given to the object is what the momentum changes by. So that's simply plus 6 Newton seconds. And again, that could also be kilograms times meter per second. It doesn't matter. So the question now is, if the object starts from rest, determine its final velocity, including magnitude and direction. All right, starts from rest, so that means V initial is 0. I'm not going to rewrite the given stuff here. So delta P equals M delta V. We know delta P is positive 6 Newton seconds, the change in momentum. We know the mass of the object is 3.0 kilograms. Change in velocity is what we're looking for. All right, so change in velocity equals 6 Newton seconds divided by 3.0 kilograms. So you get change in velocity of positive 2 meters per second. Now, I could show you how to cancel those units. I'm not going to do it right now. It's a kilogram times a meter per second squared. One of the seconds would cancel out. One of the kilograms would cancel out. You'd be left with meters per second. Good stuff. I'm going to stop there for now because the video is getting a bit long, and I do have a few more problems to do. But I'll see about shooting those later. Okay?